Today we're going to talk about strategies to address variability in nitrogen requirement. I'm Josh McGrath. I'm the Soil Extension Specialist at the University of Kentucky. You can follow me on Twitter at NPKProfessor. I do want to acknowledge the funders for this research, the Illinois Nutrient Research and Education Council and the Kentucky Corn Board generously provided funding for a lot of the research that I'll provide today, that I'll talk about today. So often when we talk about nutrients, we talk about 4R nutrient management, the right rate in the right place from the right source at the right time. But when we're talking about 4R nutrient management, we have to remember that we need to think about it in terms of the entire cropping system. So when we change any one of those factors, the other factors will be influenced. And when we talk about nitrogen, I think timing is the big lever, and I'm going to spend a good bit of this presentation covering some of those interactions with timing. But we also need to think about the performance objectives, because right is defined by the performance objectives. So throughout this presentation, we need to think about three main performance objectives that I consider when coming up with a nitrogen management plan. And that's the environmental objectives to protect water quality and air quality, economic objectives, the profitability of that cropping system, and agronomic objectives. And these performance objectives are in competition with each other. So economics, the economically optimum nitrogen rate, is not the same as the nitrogen rate that maximizes yield or that production-oriented performance objective. So nitrogen requirement is complex. I adapted this from a paper from Bill Rahn, but when we're talking about coming up with the right nitrogen rate to achieve maximum yield or maximum productivity, it is a function of responsiveness, how much yield I get per unit nitrogen, total yield potential, and the nitrogen availability from the soil. And so all three of these factors vary in space, so across the field or in between fields, and in time from year to year. The big factor here that we're very familiar with is climate. In a year where it rains more, I have a higher yield potential, right? But we also got to think about crop system, because the right nitrogen rate will change if, for example, I have a cover crop. We've seen in our research that we need more nitrogen up front, so we need to shift the timing a little bit to account for the carbon penalty in a cereal cover crop. That's real, and we do know that maybe we don't need more nitrogen overall, but we do need to have more of it put down up front to pay that carbon penalty. And in some situations, we do see that we have a higher total nitrogen requirement with that cereal cover crop. And so all of these factors are varying, and they vary independently. And so for that reason, we see that nitrogen surpluses exist. Not necessarily because we're doing anything bad, but because of the imprecision in our recommendations. So in fact, the weakness in our nitrogen recommendation systems is the reason why we have nitrogen surpluses that result in environmental impact. So when we talk about our current nitrogen recommendation systems, a lot of people say, oh, I wish we had more accurate nitrogen recommendation systems. Well, actually, our recommendations are very accurate. They're imprecise. So if we look at this figure here, we see that we have high precision is when we group our shots together. Low precision is when they're scattered out. If we look at that low precision but high accuracy, that's how most of our nutrient recommendations are. On average, we're hitting the bullseye. But in each year, or at each site, or at each spot in the field, we're not hitting the right required nitrogen rate. So we have this really high accuracy when we look at our systems, whether it's the MRTN that some of the Corn Belt states use, or here in Kentucky, we use a nitrogen recommendation system that has adjustments for soil texture and drainage, or a lot of states use a yield-based system and kind of based on the Stanford equation that we'll talk about in a little bit, but they're all highly accurate. So if we take the recommendation from the university over 20 years and we take the requirement, if we knew what the requirement was in a given field over 20 years, on average they would match up. But in any given year or at any given specific spot, site-specific spot, they're wrong. So this is a classic nitrogen response curve from a friend of mine, Bob Crowderville at the University of Maryland. And what we see is that these three sites had a very different response to nitrogen. We have two sites, the blue and the orange dots, that you can see. They, with 0 pounds of nitrogen, have very low yield. That's what we expect. But we have this one spot up here, the Keedysville site, that achieved over 200 bushels per acre with no nitrogen, actually 215 bushels per acre of corn yield with no nitrogen added. And so that's what we call a non-responsive site. It has a flat response curve. And we actually see this quite often in research. I've been doing a lot of nitrogen research with many kind of zero nitrogen plots across Kentucky and Illinois for the past couple of years. And quite often we can achieve maximum yield, 250 bushels per acre of corn with no nitrogen. But you wouldn't know that on farm because of course we're not going to take that risk of not fertilizing. So when we do research, we're going to take those out of the equation, and we come up with this modeled response curve. So that equation, actually, the y is the yield on that vertical axis, and the x is the nitrogen rate. And so we can calculate the yield at a given nitrogen rate from this modeled equation. You can see that black line strikes down the middle of the points. And so that's the average response to nitrogen across those two sites. And this is why our recommendations are accurate, because they're actually designed to target the average accurate need of nitrogen to optimize that curve. And you see that the error bars become much smaller when we drop out that non-responsive site. And the error bars are actually what measure precision, the variability around the mean. So now we're going to look at some data from Frank Cole at the University of Maryland. On the vertical axis on the left side, you see yield. On the opposite side, on the right side of that slide, you see on the vertical axis soil nitrate post-harvest in the top meter. So he went out, took a 3-foot sample, and looked at nitrate after he harvested the corn. And of course on the horizontal axis is nitrogen rate. And so with that blue line, that's the modeled nitrogen response that we talked about previously. And we see that the economic optimum yield occurred at 173 bushels per acre with 205 pounds per acre of nitrogen. Now the agronomic optimum nitrogen rate is 1 bushel higher, 174 bushels per acre, and the agronomic optimum nitrogen rate required to reach that yield was 230 pounds per acre. So we see it took 25 pounds more nitrogen to get 1 more bushel. That's why that 25 pounds doesn't pay for itself with average nitrogen and grain costs. And so then we look at the environmental optimum. So what is the environmental optimum? We don't really know, but we know we don't want to have a lot of post-harvest soil nitrate that is available for leaching or denitrification or loss. And the interesting thing is that increase from agronomic optimum or economic optimum yield to agronomic optimum yield is not really detectable at the farm gate. In other words, as a farmer, we don't know if we've hit the agronomic optimum, maximized our yield, or the economic optimum, maximized our profit. You know, we just know we had a pretty good year. And so in this case, that would be undetectable at the farm gate. That change in 1 bushel would be a loss of $5 per acre, but we don't really know if we lost that $5 per acre unless we have on-farm research that demonstrates what the actual economic and agronomic optimum yields are. But what we do see is that the environmental impact is significant. So this is an important point. Often we think that we're protecting our bottom line by protecting the environment. And while this may be true, the environmental impact is far greater than the economic impact. So there's a $5 per acre loss by going up to the maximum yield rate. We don't even know that we have it. We can't detect that at the farm gate. But in this case, there was a 17 pound per acre increase in soil nitrate in the top meter. That is significant. So we're right where that growth is exponential in residual nitrate when we're at the economic optimum. And so small changes that we don't detect at the farm gate have a big impact on the environment. So there's a disconnect there that things that don't really impact our bottom line will have a big impact on the environment. And so if we stretch this out and we look at 3 different sites and we look at what are the economic optimum yields at these 3 sites, you can see this really low yielding site has a low nitrogen requirement. That's a bad year with no rain, right? And then we got the red line, that's a really good year. And then, but actually the nitrogen rate required to get those high yields was a little bit lower at that site. And then we see this kind of moderate kind of site where we needed a little bit more nitrogen to maximize economic performance. But you look at these 3 different rates that were required at these 3 different site years to achieve economic optimum yield. But the University of Kentucky is right here in that green bar represents our range of nitrogen recommendations. So our recommendations are highly accurate but imprecise. We're kind of shooting for the middle with a little bit of confidence built in to make sure we don't miss good years. And that becomes really important when we overlay that on environmental performance, because while we have a very narrow range of nitrogen recommendations, that creates a huge range in potential environmental impact. So precision is more than just varying rate. When we talk about precision ag, quite often people only talk about variable rate, varying the rate across the field. But often precision can be changing the rate year to year, or changing the rate field to field just based on previous crop. For example, crediting a prior soybean crop, or increasing my nitrogen rate because I had a cereal cover crop ahead of that corn crop. So we need to think beyond just variable rate when we talk about precision ag. The nitrogen cycle is complex, and when we talk about precision ag, what we should be talking about is managing that nitrogen cycle and the interaction between cropping system, climate, and soil processes to more precisely target a nitrogen rate to a field, to a year, or to a spot in the field. The objective is to manage that nitrogen cycle. So I'm going to step back for a minute and talk about Stanford's equation. Recently, in the literature and popular press, some of my colleagues have kind of maligned Stanford's equation. And I think that comes from a misrepresentation or a misunderstanding of what George Stanford was saying. So he was a researcher that in the 60s, he pointed out we need to get more mechanistic in our approach to nitrogen management. And that means, accounting for different processes in our recommendations. An empirical approach is to just go out to 100 fields, put a bunch of nitrogen rates on them, and predict what the optimum rate is. Just the rate over those 100 fields that optimize the nitrogen rate for maximum yield. So that's an accurate recommendation, but highly imprecise. And in the 60s, George Stanford was saying that if we want to get more precise, we have to account for mechanisms that are associated with climate, soil type, and crop management. So the nitrogen cycle, as I said, is complex. And if fertilizer nitrogen went straight to the crop, like this red line indicates, you would see a pretty simple thing. Like we would just be able to look at per unit bushel, apply 1 pound of nitrogen or 0.6 of a pound of nitrogen. It would be a really simple thing. But the problem is the soil nitrogen cycle kind of interferes with this system. Nitrogen that we apply has to pass through this very complex system. And that's why these two figures don't look the same. So in this one figure, we've got yield versus the nitrogen in the crop, right? And so as yield goes up, we have more nitrogen in the crop. That's pretty simple. And then in this other figure, we see what the economic yield nitrogen rate was, the economic optimum nitrogen rate, and what the yield was at that point. If there was no soil nitrogen cycle, both of these figures would be a straight line. But the soil nitrogen cycle and nitrogen efficiency changes from field to field or across fields. But what Stanford's equation said in its most basic sense was that the amount of fertilizer nitrogen that we need is equal to the plant need, yield, minus soil supply. So the plant needs 200 pounds of nitrogen, I get 50 pounds from the soil, and divide it by the fertilizer efficiency. So if I surface apply urea in warm weather, maybe that's 50%. So maybe I need 200 pounds for the crop. The soil is giving me 50 pounds. That's 150. Divide it by an efficiency of 50% because I was really bad in my nitrogen management. I need to apply 300 pounds of fertilizer. But I'm just balancing the plant requirement with soil supply and fertilizer efficiency minus environmental losses. It's pretty simple. It gets more complex when we bring in these other soil processes, organic matter, soil organic nitrogen. Maybe I have manure in my system, and so I start piecing out these things. A more precise system, even if we're not doing variable rate, would give credits, additions, and subtractions for different management options, field conditions, climate, things like that. And so that's where we get this mechanistic versus an empirical model. Here's our 3 data points that we had from Bob Craddockville. And we see an empirical model would predict a given nitrogen rate that would optimize across all 3 sites. But it's wrong for each of the sites individually. On average, it's right. A mechanistic approach would look at each of the sites individually and come up with a custom nitrogen rate. And so we can't go all the way mechanistic. We just don't have enough scientific firepower yet. But we can try and move towards that mechanistic approach. So, Stanford equation provides a framework to evaluate nitrogen recommendations, to look at them more mechanistically. We do have a limited ability to estimate the components of the equation. What are the size of the nitrogen pools? In humid rain-fed environments, soil samples for nitrogen just simply don't work. In more arid climates, certainly they work, and we can use those to become more mechanistic. The rate and timing of transformations are difficult to predict because of climate interactions, but we're getting better at climate modeling. So organic nitrogen mineralization, while very good for the crop, can be very difficult to predict. And then efficiency of supply, basically root depth and how the crop interacts with the soil supply, also complicates matters. We do have some tools to help us, and I'm going to spend the balance of this presentation kind of talking about those. So how do we deal with this variability? We've set up some research here at the University of Kentucky, working also in Illinois with the Illinois Nutrient Research and Education Council and my colleague Amir Sajapur at Southern Illinois University. And for example, this figure shows one site where we have 3 different cover crops. Well, no cover crop, a cereal rye cover crop, cereal rye mixed with clover. And then we overlaid on that starter nitrogen rates crossed with side dress nitrogen rates, and then also full season nitrogen rates. The way we do this is we use a 4-row planter or nitrogen injection rig like you see here, and we put some precision ag equipment on there so that we can set up all our treatments as a prescription, run it full scale across the field, but only planting 4 rows at a time and side dressing 4 rows at a time. Using variable rate control and pumps and different tanks, we're able to go out there and switch between starter nitrogen rates in the 2x2, surface application of UAN pre-plant, and then we come in and dribble side dress with a high clearance sprayer. We started out with this design where we had a split plot. So we have all of these nitrogen rates, starter and side dress, and the split plot design we tried the first year was half of the plot got the starter and side dress that was prescribed for that plot. The other half got only starter, so we went with 0 side dress. That allowed us to look at total response just to the side dress portion. Then we got a little more ambitious in this next 2 years, and we actually split every plot into 4 subplots. And so the 4 subplots shown here on the bottom were starter plus side dress, so we got the full prescribed rate, no starter, only side dress, so we got to see just what side dress would do. And with side dress, we were coming in between V6 and V10. And then we had starter, no side dress, so we could see what would happen with just that 2x2 or pre-plant on the surface. And then we had a check. So at every spot in the field, we had a true 0 nitrogen with this new design. And so we could look at what starter plus side dress right side by side in the same tight little spatial area would do compared to no nitrogen. And so this is our rates that we use this year at all of the sites. We have multiple field sites working with cooperating farmers, and we have preseason only rates that are split in that 4 subplot design, but there we don't have numerous side dress rates. So we would have 105, 154, 204, 253, all the way up to 352 pounds per acre of nitrogen, and then the subplots got 0 or 100 pounds of side dress, just to make sure, did we maximize yield with that preseason rate? And then we also, in the same field mixed in there, we had this other kind of design where we had these 3 starter rates, about 20, 37, 55 pounds per acre of nitrogen in the 2x2. And then we had 7 side dress rates that were targeted to bring up to a given total nitrogen rate. And so those, in that split application, there were actually 21 different nitrogen rates, 7 side dress by 3 starter rates. And then we had 6 preseason only treatments. So we ended up with 57 different rates that allowed us to look at response across the field. So this is what it looks like. This is that site where we had 3 different cover crops, and we actually just finished harvesting these Saturday night before the recording of this video, 1,620 plots. That's me in the combine getting there close to the end of harvesting those plots. So we take out the center 2 rows of each of those 60-foot plots. Very big studies. We did this at multiple sites. And so what do we learn? Other factors besides nitrogen influence final yield. I know this seems simple, but often we forget to kind of highlight this important point that there is a big range of yields at a given nitrogen rate. So even at the optimum, this is data from 2018, 2019, across a lot of sites. You can see there's a ton of points, thousands of points in this model. But they converge on an accurate recommendation, that blue line through the center. But even at the optimum, there's a huge range of right rates at each spot in the field. In typical research, we consider this noise, and we just give that accurate average recommendation. But we actually want to look at these differences and understand why I required, why when I applied this much nitrogen, I got a much lower yield or a much higher yield. What are those mechanistic differences? Then also, optimum nitrogen rate varies across and between fields. So again, this is multiple fields and multiple points within each of those fields. And we saw that at different places in the field, we needed different nitrogen rates to achieve maximum yield. There's a big range of right rates. So when we get back to the 4 R's, the right rate is very variable. And this is determined by yield and site-specific response. So soil and supply could be a part of it, which is not just what's in the soil, but also does the plant have big, deep roots, or was it a very shallow soil, so supply wasn't that good. That responsiveness versus yield potential, they're two different things. And so yield response across sites, pre-plant N and cover crop last year, our economic optimum nitrogen rate was 268 pounds per acre, 231 bushels per acre, right? So that sounds pretty good, all right? We've got a number, we can make a recommendation. But if I split out cover crop, if I split out sites, I'm not even changing out the amount of starter range, just looking at it, what was the optimum each one of these sites and each one of these cover crops, all of a sudden I've got a big range of right nitrogen rates. And then if I split out site, cover crop, and pre-plant N, my economic optimum yield ranged from 128 to 342. My economic optimum nitrogen rate was between 100 and 330 pounds per acre. So I had 231 pound per acre range in right nitrogen rates when I split out by site management. These things really have a big impact on what the right rate is. So this makes that case for a more mechanistic approach. So when we look at site-specific nitrogen, there's two ways to go. The predictive approach, which is works, I think, fine for things like phosphorus and potassium, where maybe you can take a soil sample and map, and at the beginning of the season you have a map that says this is where I'm going to put different rates of nitrogen. And this works when we're working across different fields. You can say this field's going to get 180 pounds per acre, this field's going to get 200 pounds per acre, based on history and some things like that. But I think if we want to do real precision ag within the field, we have to get to this reactive approach, where actually at the beginning of the season we don't know how much nitrogen we're going to apply. But the reactive approach responds to need expressed by the crop, and it's going to rely on things like sensors or imagery to come up with the right rate. But key to the reactive approach is in-season nitrogen management. So all of a sudden timing becomes very important. A reactive approach means that you have to be splitting your nitrogen and doing side dress. Now some people, when they talk about side dress, they mean I'm going to plant the corn and then I'm going to come in and put down nitrogen when that corn is, very small at like V4. But that's not what I'm talking about when I say, or V2, excuse me. When I'm talking about side dress, I'm talking about coming in post V4, probably V6, V8, and side dressing much later in the season. So I need some starter nitrogen out there applied to get me to that V6, V8 stage, right? And then I'm going to put the balance down at side dress. And what that allows is for that crop to express need, for me to look at variability across the field. And even if I'm not doing variable rate in the field, I can still look at how's my weather been to this point. I haven't exposed myself to risk by applying all of that nitrogen up front. I've eliminated that risk. And now I'm going in when the crop is getting ready to take up most of the nitrogen, and I'm going to kind of deal with that need that I see based on the first 30 to 40 days of growth. This is really a combination of that predictive and reactive approach, because I had a plan at the beginning of the season, and then I'm going to come in 30, 40 days in and react to how the conditions changed. So the total nitrogen requirement is a function of starter plus that pre-plant surface applied and then in-season nitrogen. It's predictive and reactive. And I want to be really clear, because a lot of people also think about side dress as a rescue application. That's not what I'm talking about here. I'm talking about a plan for the total nitrogen requirement for the season that I had at the beginning of that season when I planted the corn. I had a plan to split it up between different timings of application, and I want to put the bulk of my nitrogen down close to that rapid growth stage that we see in this figure. So what are some of the tools that I have to manage nitrogen in season? I've got the PSNT, the pre-side dress soil nitrate test. This is a great test. It's actually probably one of the best correlated soil tests that we have. It's underutilized, but really I only recommend it when I have a large organic end source, either because I had a legume cover crop preceding my corn crop, or I applied manure to that corn crop in the spring. The PSNT does a great job of looking at that organic supply and how it's going based on the weather. So you come in when that corn's about 12 inches tall, You take a 12-inch soil sample, and if it's over 20 parts per million, plus or minus, different universities use different numbers, but somewhere around 15 to 25. Above that, no side dress needed. Below that, stick with your nutrient management plan that you started with at the beginning of the season. The chlorophyll meter is labor intensive. We've seen some movement away from this, but you come in there in that crop around the 6th leaf stage, you clip it on the leaf, and you look at the chlorophyll content of the leaf, but you have to have a reference strip. So I like to have a strip in the field where at the beginning of the season I applied a full season rate of nitrogen. So let's say your full season plan is 200 pounds per acre. You started off with 50 pounds of starter on the whole field. You've got to have some area of the field that you already put down 150, 200 pounds on to compare the rest of the field against. It's a good diagnostic test like the PSNT, but you've got to sample a lot of plants. The NDVI sensor. We now have handheld NDVI sensors like Green Seeker that you can walk out across the field and get measurements like you would with the chlorophyll meter. Again, requires a reference strip. But we also have sprayer or fertilizer applicator mounted sensors like Green Seeker, Optrix by Ag Leader, the N sensor by Yara that allow us to respond and do variable rate in real time as we travel across the field. I'm going to talk a little bit more about that. Late season stalk nitrate test is not really an in-season management tool. It's a post-season kind of looking at how did I do. Very good in manure systems. Am I over-applying nitrogen? That's what it tells us. It doesn't tell us if we under-applied. You go out and take that corn stalk sample, look at nitrate in it, and if the sample comes back over 2,000 parts per million, you probably have more nitrogen than you needed in the system. Now, that could be because you had too much fertilizer out there, you didn't correctly predict how much nitrogen you were going to get out of your manure, but it also could be because you didn't yield enough. In a drought year with very low yields, where I fertilize for maximum yields, we see very high corn stalk nitrate tests. Reference strips, this is super low tech, but just like with the chlorophyll meter or that handheld NDVI sensor, you go out and you put a couple strips in the field with 200 pounds of nitrogen. You've got your 50 pounds of starter on the rest of the field, and you can visually observe what does the rest of the field look like compared to that strip that had that maximum rate up front. So very valuable. I do want to caution you that small corn tissue testing doesn't work. Quite often I have growers come to me with results of nitrate or total nitrogen in V4. Well, that plant is getting ready to go into rapid growth stage, and so that number is extremely variable and can change throughout the day at that growth stage. And so these numbers are useless. And here's some data that compares the yield, relative yield, against that small tissue, small plant nitrogen content, and there is no relationship. So tissue sampling for nitrogen early in the season is a non-starter. It doesn't work. Now here's corn stalk nitrate test on the top. Here's the PSNT on the bottom, a lot of data, but that's just to show what a good relationship looks like. Great test, work well. Labor intensive, I think underutilized. I really recommend them in manured systems if you're trying to dial in your program. Now I'm going to spend a little bit more time on the sensors. Not advocating that you should go with one brand or the other. That's not the deal here. I've worked with this one brand just because that's what we had to work with, but I want you to think about the philosophy when I'm going through this. So this is an example from the Mid-Atlantic, but you're going to need local recommendations to make this work. You can't just adopt something from geographically far away. But sensors use models and plant response to early growing conditions to adjust rate both spatially and temporally, so each year and across the field. It requires that local algorithm, and you can see here we mounted them on a spray boom, and they're sensing that crop, and every second the computer is changing the rate based on what it sees in the crop. Now it requires a reference strip, and it uses that reference strip and the reading of the crop to address yield potential and nitrogen responsiveness independently. So just as a reminder, nitrogen responsiveness is how many bushels per pound of nitrogen, right? And so responsiveness is this key component that as we move across the field and addressing a variable requirement. And so there's a yield prediction made based on a vegetative index like NDVI. So most of these sensors use some sort of normalized differential vegetative index based on near infrared, red, or maybe red edge, and they're making this yield prediction. In the Mid-Atlantic, what we used was a yield prediction and this response index. So the response index is created with reference strips. You can see in this field that we have a spot where no pre-plant nitrogen was applied, and it's a little bit harder to kind of see in this image, but in front of that is an area where we applied excess nitrogen pre-plant. So we've got no nitrogen at planting up until side dress in a small strip, and then excess nitrogen. And the high reference area NDVI divided by the low reference area gives us that response index. So if the plant is twice as big with the excess fertilizer, the response index would be 2. And we use a yield prediction of, okay, what if I don't fertilize? So the first thing the computer does is calculate at this spot based on the NDVI, so NDVI on the horizontal axis, predicted yield on the vertical axis. The computer is taking an NDVI reading every second and predicting what would the yield of this plant be if I don't apply any side dress right now. So we're going in at V6 to V8 and sensing these plants and saying, what would the yield be if I don't apply any side dress? And then it predicts, based on this equation, the yield if I do fertilize. And here's where that response index comes in. So it's basically takes that yield equation, it has some coefficients that are locally determined. It takes how many days since planting to the date of sensing and fertilization. Again, the response index, in this case for this field, the response index was 1.5. You can see the high reference measured 0.75 and the low reference was 0.5. And that algorithm is predicting the yield with side dress. And look at the blue line and the pink line, and you see there's a difference as we go across the NDVI. And so responsiveness is the yield with nitrogen, YPN, minus the yield without nitrogen, YP naught. And the user has to say what's the realistic maximum yield for this algorithm, because you can see it goes up to unrealistic yields. And so the user kind of supplies that that maximum realistic yield, and then the equation looks at, response, total response. So what we see is that the difference between the two, and we take and multiply that times the nitrogen content in grain, and we put in a nitrogen use efficiency number, and we get up this kind of total nitrogen requirement. We take and we look at the nitrogen rate, the yield with nitrogen, the yield without nitrogen, that difference, times the nitrogen content in grain. So how much grain do I get if I fertilize? How much nitrogen is in that grain? And that gives me the total nitrogen rate required by the plant. On the end there of the equation, you see that we realize that there's a certain amount needed to kind of kickstart the system. And then we divide that by nitrogen use efficiency. And this is the user supplies this number. But basically, what we've done is using these sensors and these yield prediction equations, we have come up with Stanford's equation, because the yield without nitrogen is the nitrogen supply from the soil. The yield with nitrogen is that N crop from Stanford's equation, and then NUE on the denominator. And so basically the sensors are calculating Stanford's equation. They're becoming more mechanistic. Again, there's imperial relationships involved, but they are more mechanistic. A personal note, we've got to kind of trust the science if we're going to use the science. Everyone on both sides of these arguments likes to say that they are trying to be science-based. And I did a lot of work in the Mid-Atlantic with these sensors. And when we first started out, it was kind of funny. So the way the nitrogen recommendation goes is that the NDVI, you see here on the horizontal axis, the higher the NDVI, the bigger the plant. The better the growing conditions in that area of the field. And you see the nitrogen rate on the vertical axis. And so this system saves nitrogen by applying a lower rate where the yield potential is lower. YPO, the yield with nitrogen and the yield without nitrogen are closer to each other. It's not as responsive, and yield is less, so we have a much lower rate in the bad areas of the field. Then kind of that middle area of the field, we apply a maximum rate, higher than what the university recommends oftentimes, so higher than university recommendations. And then in the very best areas of the field, because of the way the equation works, we substitute in that maximum realistic yield, the rate actually comes back down. And we see this in our current research, that the very best areas of the field really don't require very much nitrogen at all. They're good areas of the field, and so that good soil is growing that plant. And so we cut the nitrogen rate in the best areas of the field, the worst areas of the field, and maximize the fertilizer nitrogen in that middle range, which is counterintuitive to some people. So the environmental folks, where I used to work in Maryland, they wanted to cut off the green seeker and only allow it to apply up to existing university recommendations. And some of the farmers I would talk to were very happy when it allowed them to apply extra nitrogen. They said, but I don't want to go below what I was doing before, which I'm actually fine with, because I think eventually, if they try the technology out, you'd see that it works, and then you'd start to trust the technology. And I always try and make that argument that if you trust the technology here, you've got to trust it up here at the top as well. So what can you do? All right, we've talked about how extremely variable nitrogen requirement is. We've talked about some of the tools that are at our disposal. I showed you some of our research that shows this huge range in right nitrogen rate, especially when we modify management like cover crop or starter rate. And so to do better, you need to take an active approach at nitrogen management. You need to use all the available diagnostic tools that are appropriate in your situation. If you have a local algorithm, or get that handheld sensor and start using it to just look at differences in the field. You need to ask yourself, what factors influence nitrogen requirement? My crop system, what kind of cover crop am I running? What was my previous crop? Timing is the biggest lever in nitrogen management. So the first thing I would do is switch to a side dress dominated system. Maybe not all of your acres, maybe some acres that you think specifically are very variable, but go to most of your nitrogen being applied in season so that you have time to kind of assess the situation. Modern equipment allows us to get across ground a lot quicker, and so this isn't as much of an obstacle as it was 20 years ago. Think about placement, source, soil, topography. We see slope and elevation have a huge impact on nitrogen requirement here in Kentucky. And then, of course, weather. So if you're using a zone-based approach for nitrogen management, technically, I'm not a big fan of that, but there are things, soil topography and soil texture that do influence nitrogen requirements. But you have to question, I don't think we provide very good guidance. There's not good science on this yet in most areas, especially rain-fed areas, of how those zones control nitrogen requirement. But, you can zone the field out and think about it in that context. I will caution that we started out using yield-based approaches for zones, so we would come up with these yield zones, and that never worked. And you can see that with that kind of green seeker algorithm, that's very counterintuitive versus yield, that there's kind of high yield needs less nitrogen, low yield needs less nitrogen, and that mid-range needs the highest nitrogen. And that's probably why we never saw that yield zones work for nitrogen management. I would strongly kind of caution you not to try yield-based approaches to precision management. So what else can we do? Consider these reactive approaches like using sensors, using chlorophyll meters, using handheld sensors, or top of the pyramid, going in with a local algorithm that addresses yield response, yield potential, and changing that rate every second as you travel across the field. That's kind of the top of the mountain. But the adoption curve is steep, so just move into it, come up with a plan, multi-year plan, and ease into it, because I saw many people kind of jump right in with the sensors, and they had so many problems in the first year that they just ended up on a shelf in the shop and they didn't really use them to their maximum potential. You can start by just mapping the field and looking at how NDVI changes across the field. Use some of your software to look at those zones and kind of see what things are influencing the NDVI. Use local guidance. I'm really an advocate of using a local algorithm. And consider competing approaches. An approach that I didn't talk about is the sufficiency index approach. What I talked about was the response index approach, but I really do think that you need to consider all of your options. And then finally, with nitrogen management, replicated, randomized strip trials are extremely valuable, and you can set those up with your technology to kind of evaluate what you're doing as you're going along. So with that, I thank you. This is my contact information. Feel free to reach out to me by email or follow me on Twitter. Thanks.